You're welcome once again to this new episode. This is Solomon at Solo for Math. We are continuing with differentiation, and today we want to look at first principles. Differentiating from first principles. Alright, we need to know where the formula comes from. Yes. So we are going to look at a function. I've brought it here, a function. Let it be, this is a curve showing a function y equals to fx. It's a function of x, a general function. And if this is a point, for example P here, and this is a point Q on that curve, like this line here crosses the curve at point P and Q, and we know if we are to get the derivative, or to differentiate, it's like getting the gradient. And we know that a gradient of a line is got from a change in the y values, any two y values on the line, over the change in any, or a difference in any two values of x, giving us dy dx. That's why we call it dy dx. So if you want to get the gradient of a curve, we always approximate it to the gradient of a line. Okay, we want to approximate it to the gradient of a line, and we always say that the gradient of a curve at a given point P is always equal to the gradient of a line, or the tangent. Actually, it's equal to the gradient of a tangent at that very point P. Now, you realize that if you have a point P and you have another point maybe there on this line, then you can get the gradient of this line. Okay, by just substituting maybe y2 minus y1 over x2 minus x1, where maybe this is maybe a point x2 y2, and then maybe this point is x1 y1. So when you subtract the two, get y2 minus y1 over x2 minus x1, it gives the gradient. And we're saying that the gradient of the tangent is the same as the gradient of the curve at that point P. Okay, now we are saying that if we approximate the gradient of the curve to be equal to the gradient of this line, it is not so accurate, because we only know of one point on the curve, and then the other point we're just choosing it on this line, so we cannot say that is to accurate. So for accurate results, what we do, we choose 2 points on the curve, like we have point P and we choose another point Q. So when we join these 2 points, and the line of course extends far beyond those points, then if we can get the gradient of this line here, okay, if we can get the gradient of this line here, then we may be sure that that is an accurate, at least an accurate gradient, because we at least have 2 points on the curve, okay, which are also giving us the gradient of this line PQ. So meaning, if I take this point to be, forget about this one, let this point be x, so it means it gives us a corresponding y value of fx. If our function is fx, then when we feed in x, it gives us our y as fx. Then if between x and point q we consider that to be a small change in x, then it means if from here up to here there's a small change in x, represent it like this, then it means this point here will be x plus small change in x. Then it means that our f value here, our y value here, will be f into x plus a small change. Yeah, if you have y equals fx, if you have the x coordinate, then substitute in the function, it will give you the y coordinate. So that is it. So in this case, if we were to find the gradient of this line PQ, then we would say that dy dx is equal to a change in y values. The y values are these, so we would say f x plus small change in x minus fx over over a change in the x coordinates. So this would be like x plus this one. This one was corresponding to fx plus the x minus x, which we can simplify as fx plus a small change in x minus fx over, these ones cancel out, so remain with a small change in x. Alright, now, but remember, we want to get a more accurate value. So since we said that the gradient, if we have that assumption that the gradient of the curve is always equal to the gradient of that tangent, a tangent to the curve at point P. Okay, since we don't know, we didn't take this because we were choosing the value, this other value of the other point on the line arbitrarily. We don't know what exactly it is. So if people choose different points, they end up with different values. Okay, but if we have this, if we know this and this, we know those are points on the line, on the curve, and as well on this line. So if we get the gradient of this curve, of this line, then how would we get the gradient of the curve? So from this, we have a single step to go. We are saying that if we bring this point Q a bit close, assume it was here, maybe let me name it point Q3, and we draw a line joining P and Q3. You see, it is a bit close to this line here. Let me name it MN. Okay, so the condition that gives us a gradient or an accurate gradient is we should have an approximate line joining P and Q that is almost close or equal to this line MN. It means we must bring this point Q close. Assume I bring it here. You see the line I join through that, the P and Q will be a bit close, and if you bring it more close, you find that at a certain point this line PQ will be equal to the line MN. Okay, so that's where we get the condition for the limit. So we say that the gradient dy dx is equal to a limit as the small change in x tends to 0 of the function evaluated at that minus function of x over small change in x. So by bringing q close to p, like here, bringing q close to p, we are trying to reduce this dx. Okay, and the more you reduce it, it is tending to 0. And we said as it tends to 0, it means that that gradient pq is almost equal to the gradient of this tangent here. Okay, and since we say that always the gradient of a tangent is equal to the line, to the gradient of the curve at that point, then it means if we reduce this point Q to come close to P, the more we reduce it, the gradient of that line PQ comes close to a point, to the gradient of line MN, and at the point of coincidence, then we know we have some accurate value of our gradient. So this is the formula that we use when differentiating from first principles. Let's look at examples. Differentiate from first principles, we are going to look at this. 1, if you have y equals to x squared. 2, if you have y equals to 2x plus 1. 3, if you have y equals to x to the power 4 plus 3x squared over 2x squared. And lastly, 4, we shall look at a function 3x squared minus 2x plus 4. Alright, let's move on. Roman numeral 1, we have y equals to x squared. So having y equals y equals to x squared is the same as saying our f of x is equal to x squared. So if you have fx as x squared, remember our formula. Let me write it here. That divide x is equal to a limit as the x tends to 0, fx plus dx minus fx over dx. This is our formula here. So it means we need x plus a small change in x. These are functions. If you remember functions, if you have fx as this, then it means wherever there is x, put x plus dx. So it means our function will be x plus dx squared. We can expand this to give us x squared plus 2x dx plus dx squared. So let's substitute in our formula. So meaning our dy dx is equal to a limit as small change in x tends to 0 of, our formula is this. You can always write the formula over dx. Let's substitute limit as dx tends to 0 of, what is our fx plus dx? It is this, x squared plus 2x dx plus dx squared minus, what is our fx? Our fx is x squared over dx. So we apply the limit after simplifying where possible. Then this is equal to limit as dx tends to 0. Of course, this one and this goes. So when we divide, this will be 2x. These ones will cancel, so remain with 2x plus, and this one will be dx squared over dx, which gives us dx. Now at this time, we can take the limits. So like when dx tends to 0, this goes to 0. So like this will be equal to 2x plus 0, like we've taken the limit, which gives us our dy dx equal to 2x. And if you differentiate normally, you see that we end up with that very answer. Alright, let's look at number 2. Y equals to 2x plus 1. Maybe what do we expect? We expect our dy dx to be equal to 2. So we can always work towards getting what we expect. So meaning our fx is equal to 2x plus 1, and our fx plus equals to, substitute where there is x, put in x plus dx. So we have 2 into x plus small change in x plus 1. When we expand, this will be 2x plus 2 dx plus 1. So let's substitute in our formula. Y dx equals to a limit as dx, small change in x, tends to 0, of what is our fx plus d theta is this, mean dx, it is this, plus 1 minus fx, which is 2x. Remember, let me put a bracket here so that that negative shouldn't confuse us, over the small change in x. We said apply limits after simplifying. If you can divide through and remain with terms that have no dx, then you go on to apply the limits. So when we expand this, you see this is 2x plus 2 dx plus 1 minus 2x minus 1 over dx. So you will see that this and this will go, also a 1 and this will go. So we remain with a limit as small change in x tends to 0 of, this will be 2 dx over dx. So the dx goes, and this one will be equal to a limit as small change in x tends to 0 of 2. Now a limit, wherever the x goes, for a constant, it will remain that very value. Okay, because we don't have the x here, so it is a constant. Whether x, the small change in x is 1000 or 0 or whatever, it will remain true if it is a constant. So that is the answer we expected to get. Number 3, have y equals to x to the power 4 plus 3x squared over x squared is a 2x squared. Alright, this one we can start by simplifying. Okay, so we can also relate it to fx, it is a function of x, and when we simplify, you see this one is the same as, like, I can factor out x squared up here, so that I remain with x squared plus a 3, then over 2x squared. Now this can go with this, so I remain with a half x squared plus 3. So what is our fx plus small change in x? This one is equal to a half, where there is x, put x plus small change in x squared plus a 3. When we expand, this will be x squared plus 2x dx plus small change in x squared plus a 3. Yes, so we substitute in our formula, dy dx goes to a limit as x, dx tends to 0 of fx plus small change in x, which is this, that is a half x squared plus 2x, small change in x plus small change in x squared plus 3 minus fx, which is this, half into x squared plus 3 over everything over the x. Alright, so here you realize that meaning the y dx equals to a limit. We said first simplify as the x tends to of, when we can take this half out because it is common. We have a half here, we have a half here. I can take it outside the bracket, so we have it maybe here. So what do we remain with in the bracket? We remain with x squared plus 2x x plus the x squared plus 3 minus, now this minus, when we open a bracket, this will be minus x squared, then minus 3 over the x. So this will go with that, this will also go with this, so we remain with a limit as small change in x tends to 0 of a half into what remain within bracket. We have 2x x plus a small change in x squared over the x. So when we divide, simplifying further, we have a limit as the x tends to 0 over half, and this one remains 2x plus a small change in x. So when we take limits, when the x, the small change in x goes to 0 or tends to 0, then we shall have a half into 2x plus a 0, which is half times 2x, giving us x. And at least that is what we expect. Yeah, looking at the last example, number 4. If we have a function of x equaling to 3x squared minus 2x plus 4, what is our fx plus a small change in x? Substitute 3 into x plus small change in x squared minus 2 into x plus a small change in x plus a 4. We can expand so that it becomes very easy. When we substitute, this will be 3, this one is x squared plus 2x dx plus small change in x squared minus, this will be 2x minus the x plus a 4. Okay, there's a bracket here, yes. So can have 3x squared plus, this is 6 x dx plus 3 dx squared minus 2x minus x squared, sorry, minus dx plus a 4. Sorry, there's a 2 here. There's a 2 here and a 2 there because we expanded here. Minus 2x minus 2 dx. Yeah. So let's substitute. So dy dx equals to a limit as a small change in x tends to 0 of fx plus dx, which is 3x squared plus 6x dx plus 3 dx squared minus 2x minus 2 dx plus 4 minus this will be 3x squared. This will become a plus because it was a minus, then plus 2x minus 4. Then all of this is over a small change in x. We said apply the limit after simplifying. So the limit, what cancels out, we know this and this will go. What else? We have this and this also going. We have a 4 also going. So we remain with this. Let's also divide by dx. So this divided by this remain with 6x. Then this by this remain with plus 3 dx. This to be minus 2. Now if we take limits now, this will be 6x plus this is a 0 minus 2, giving us a 6x minus 2. Or someone may choose to expand, to factorize, so you have 3x minus 1 as required. Thank you for watching. The next episode will be about differentiation from first principles of trigonometrical ratios. Don't forget to subscribe, to share, to like, and to comment. Goodbye.